So we have learned about the inverse transform technique, and we have said that if you want to convert a random number into a random variate from a specific distribution, you need to use the inverse CDF of that specific distribution. Of course, that should be a continuous random variable. I mean, up to this point, we have only practiced the generation of continuous random variates. So the inverse CDF, when available, it can be useful to convert the random number into a random variate. So this is the story of the previous videos. Now we are going to learn how we can use the inverse transform technique to generate random variates from the normal distribution. Now, if you remember, the normal random variables can take any real value. There is not a boundary defined for them. So unlikely to the uniform or triangular or exponential distribution, normal random variable is one of the random variables which can take any real value. The probability density function has a bell shape like this, and it is unbounded from both sides. However, because the tails are converging so fast to zero, practically a normal random variable can take values within plus minus 6 sigma boundaries. So the sigma is called the standard deviation of the distribution, and mu is called the location parameter or the mean of the distribution. The PDF is symmetric around the mu value, and sigma basically determines the standard deviation. Sigma square is called the variance. So the spread of the possible values of this random variable is determined by the sigma itself. So for a large sigma, the possible values of this random variable are also going to be far from each other actually. So the cumulative distribution function theoretically must have a shape like this letter S. So you see, if you move from minus infinity to plus infinity, the cumulative area under the PDF on the left-hand side of your point is just going to increase slowly in the beginning. Then because the PDF gets larger, it is going to be fast and fast. The largest increase speed in the cumulative area on the left-hand side is just going to occur at the mode of the function. So the cumulative area is going to increase slowly, then fast. The maximum increase speed is going to be obtained here. Then the area is going to continue again as you move away from mu in this direction. But the rate of cumulative area increase will get slower and slower. And as you move to infinity, it will become too slow. And in the end, when in infinity, the CDF will converge to 1. You know, the cumulative distribution function is obtained through integration of the probability density function. You see, for normal random variables, we have an exponential function in the PDF, which has a quadratic power in terms of variable x. So the power of the exponential function is quadratic. Therefore, it is impossible to integrate such a function. And therefore, we say that the CDF is not available. Now, we know this fact from probability theory. At this point, for practical purposes, how can we use the normal distribution or the normal random variable to model the inputs of a discrete event system model? Now you see, mostly the activity duration times and demand are modeled with a normal random variable. It's a very, very practical situation that the activity duration times or the demand are normally distributed. Why? Because you know, according to the central limit theorem, the sum of a large number of independent random variables should be normally distributed. So this is what the central limit theorem states. Now you see, the activity duration time for any activity, imagine you are just going to visit the hairdresser shop for a haircut. Now a haircut operation consists of too many but short tasks, right? Now first they comb your hair, then they just make basic cuts, then they shorten your hair, and so on and so forth. I do not know the details of a hairdresser procedure actually, but any activity consists of many short tasks. And these short tasks are independent from each other usually, and they take a random amount of time. Therefore, the total duration of a haircut operation should be normally distributed according to the central limit theorem. Or when you visit a bank and just you want to withdraw money, in that case, there will be too many tasks that are needed to be performed by the teller, right? So first of all, they are just going to collect that amount of money. They are going to count that amount of money. They are going to prepare a receipt for the operation. They are going to make you sign that receipt, so on and so forth. So all of these small tasks, which consist of a short amount of time, they have random durations. And the total withdrawal operations duration is the sum of these short durations. Therefore, the activity duration times are typically following the normal distribution. The demand itself as well. Now, what is demand? The demand to any product in a supermarket, for example, is basically the sum of independent demand of many customers, right? The total demand on any day is determined by the demand of each visiting customer to that product. So basically, the demand is sum of individual demands. And the individual demands are usually independent from each other. Every customer behaves independently. Therefore, the demand to a certain product can also be distributed normally. So the normal distribution is a very typical distribution to model the input variables such as demand or the activity duration times in discrete event system simulation, and therefore we definitely need to learn how to generate random variates from this distribution. How can we convert the random numbers to random variates from normal distribution? Now the problem is the CDF is not available. If the CDF is not available, nor its inverse, right? So we do not have the inverse CDF. So if we do not have the inverse CDF in the closed form, how can we use the inverse transform technique? Now, we know that from the probability course, the CDF of normal random variable is approximated numerically. And if we want to calculate the probabilities for any normal random variable, we were using the CDF table for standard normal distributions. So what was the procedure again? We were writing the probability statement for a normal random variable. Then we apply standardization by subtracting the location parameter and dividing the scale parameter of the both sides of the probability statement. Then we convert that probability statement to another probability statement that is related to a standard normal random variable. So usually we call this transformation the Z transformation. Actually, this should not be called Z transformation. We should call that standardization. So we standardize the normal random variable and the regarding probability statement. Then for a probability statement that is related to standard normal random variable, we were identifying the corresponding probability from the table, right? Now, we are just going to do the inverse operation this time. So we will be given a probability this time, which is in the form of a random number. So the random number will be indicating the cumulative probability. And for that cumulative probability, or for that random number, first we are going to identify the corresponding Z quantile in the standard normal distribution. Then using that Z quantile, we are going to multiply it with the standard deviation and shift it with the location to convert it to the random variate, which is supposed to be generated from the normal distribution. So here's the algorithm. Now you see we have this standard normal CDF table, which I am going to show you right now. So we have this table. Now you see this table shows only cumulative probabilities which are greater than 0.5. So that is unfortunate, because if our random number is greater than 0.5, then we can safely use this table to identify the Z quantile, which is X here. However, if the value is Z than 0.5, what we are going to do? Then we are going to use the symmetricity for this PDF of standard normal distribution. So how does this work? So it says, if we want to generate a normal random variate with location parameter mu and variance sigma square, with mean mu and variance sigma square. Now remember, if it says variance, we need to identify the standard deviation by taking the square root of the variance. Now the algorithm is as follows. If your random number is greater than or equal to 0.5, then we are just going to use the CDF table directly And we need to find the Zi value, the critical Zi value for which the cumulative probability in the standard normal CDF is equal to that Ri value. Now, for example, if the Ri is 0.7673, in that case, the corresponding Z value will be 0.73. Then after identifying that Z value, we are just going to multiply that Z value with the standard deviation sigma and add mu, shift this value with mu, and that is just going to be Xi value, which is the random variate that we want to generate from that normal distribution. However, if the random number is less than 0.5, it is impossible for us to identify any critical Z value for which the cumulative probability is a value that is less than 0.5, right? So we are just going to use the symmetricity of this table. And first we are going to calculate 1 minus Ri. And for 1 minus Ri value, we will find the critical Z value. Now you see, for any critical Z value that is the quantile of 1 minus Ri, by the symmetricity of the standard normal PDF, we are going to take its negative, the negative version, and for the negative version, the CDF will be equal to Ri. Because if the area on the left-hand side X value is 1 minus Ri, this means the area on the right-hand side will be equal to Ri. And due to the symmetricity, the area on the left-hand side of minus X will be Ri as well. So basically, if the random number is less than 0.5, first you calculate 1 minus Ri, the complement probability, and then search for the critical Z for that value. Then you take the negative of that Z value. Therefore, the generated random variate will be calculated as mu minus sigma times Zi. So this minus sign comes from the symmetricity operation. So this Zi value is not the Zi that we are looking for. We are actually looking for its negative, and this negative sign indicates that. So let's practice this. It says the service time of tellers in a bank is normally distributed with mean 7 minutes and variance of 2.25. Now you see, if the variance is 2.25, you can easily calculate the standard deviation equal to 1.5. Sigma will be equal to 1.5. It is not sigma square that we are going to use. We will use the standard deviation in the formula. So again, we are going to use these two random numbers to generate service times for two customers. Now, R1 and R2 are here. Now you see, my first random number is less than 0.5. What am I going to do? I am just going to calculate 1 minus R1, which is 0.8825 in this case. And I will identify the critical Z value for 8825. So let's check that out. So for 8825, which is somewhere between these two values, right? 8825 is somewhere between these two values. So it is not 1.18 or it is not 1.19. I think it should be 1.1875. Okay, 1.1875, or approximately we can say 1.185, just the middle value between 1.18 and 1.19. However, we should not do it like this. So for 8825, I think we should choose 1.1875 as a better candidate. However, such small approximations can be made in any way. Now for 1.185, we need to use the mu minus sigma times Z1 formula, because this is not the actual quantile that we are looking for. The actual quantile that we are looking for is the negative of this one, because the area on the left-hand side of minus 1.185 is equal to 0.1175. So we are going to use 7 minus 1.5 times 1.185, and that result is 5.2225. You see, when the random number is less than 0.5, we generate a random variate which is less than the mean. If the random number is greater than 0.5, then the generated random variate will be greater than the mean. Okay, I mean, this is how you can check your results. If the random number is less than 0.5, then the random variate would be less than the mean. And then if it is greater than 0.5, it should be greater than the mean. Now you see for this second random number, which is greater than 0.5, I can directly identify the z value. Let's do that for 0.6046. Where is that? 0.6046 is somewhere between these two values, right? So let's take the average. It is not 0.26 or 27, it is just between. So we take 0.265. And then the second random variate will be location parameter plus the scale parameter sigma times z2. So there is a plus sign because the number was already greater than 0.5. And you see for the second operation, the duration of the service is going to be 7.3975. So the service time for the first client will be 5.22 minutes. The service time for the second client will be approximately 7.40 minutes. So this was just a practice of the normal random variable. By the way, I need to change the header here. It should not be triangular random variable. It should be normal random variable. I'm going to change that and re-upload the document. And one more thing that I would like to show you. Now you see this is the primitive way of generating random variates by using this CDF table, but the primitive ways are always helpful to learn the theory. Okay. If we are going to practice this in a spreadsheet simulation, if we want to convert my random numbers into random variates which are coming from the normal distribution, what you can do is in Excel, you can use norm.in function. Basically, it says, as you can see here, it returns the inverse of the normal cumulative distribution for the specified mean and standard deviation. So you open parentheses, you say, this is going to be my probability, and I'm just going to write A2 here. So for the random number in the previous cell, and the mean of 7 and the standard deviation of 1.5, it will generate the random variate. Now you see these two values, 5.22 and 5.39, which are very close to our results in the presentation. Now you see why we have the exact 5.218 here, but we have a different result here, because you see we have made an approximation error here. What I have told you was we should use 1.1875 instead of 1.185. So instead of the intermediate values, you need to apply a correct linear approximation between the two close values in the table. So remember, we have told that these two close values are somewhere between these two, and 0.8825 is much more closer to 8830 than 8810. So therefore, by the linear approximation, the Z quantile must be much more closer to 1.19. So I would choose 1.1875 in that case. And in that case, the resulting random variate would be much more accurate than the one that we have written here.